Hello everyone, and thank you for joining us today. We're excited to bring you this overview webinar on Optimal Power Flow, or OPF. Reliable, secure, and efficient operation of power systems is becoming increasingly important due to drastic changes in technology and industry structure. Optimal Power Flow enables you to improve electrical and financial performance of electrical power systems while maintaining system resiliency and security. So let's get started and learn more about optimization studies using Optimal Power Flow. Today's agenda will include some definitions and concepts of optimal power flow, the challenges and significance of performing these studies, the actual analysis itself along with its applications, and of course we'll go through some examples in ETAP software. Why do we need to optimize our electrical system? We of course want to reduce installation and operating cost, improve system performance, and of course improve reliability and security. We want to do this through design as well as operations of electrical power systems in order to achieve these objectives on a continuous basis and throughout the life cycle of your electrical system. There are multiple optimization benefits that apply to multiple industries. Not only power generation, but also power transmission, industrial facilities, and microgrids. All of these different types of industries, and not just limited to these, can benefit from an optimization study using optimal power flow. We can of course do our optimization using load flow solutions. In load flow, we are generally given megawatt and voltage of our power generating system. We also know our loading levels, and we can control certain settings such as load tap changers on transformers, capacitor banks, and many more. The load flow solution itself is an iterative process. We can solve our bus voltages and branch flows, check the under and over voltage conditions as well as device overload conditions, change controls again such as tap changers and capacitor banks, run the load flow, and observe whether the system is now optimized. And if it's not optimized, we essentially iterate and solve the bus voltages and branch flows again, change our controls, and continue with this iterative process. So therefore, we can actually use load flow through an iterative process to optimize the electrical system. But because it takes time and understanding of your electrical system and there's many combinations, it's not the preferred approach. There's a need for a more approach. And in order for us to use an optimal solution, there are certain requirements that we would like this optimized approach to have. We must be able to get direct solutions instead of a load flow iterative process. It must be able to solve AC power flow. That means we solve for megawatt and megavar. That means we're optimizing real and reactive power both. We should be able to optimize various system conditions. We should be able to automatically get the adjustments on the control variable settings, and the optimized solution should honor system constraints. If you look at an objective function such as yx is 20x squared minus 80x minus 10 and graph it, you'll essentially see this beige or brownish color line, and if you apply the control variable range, that is the constraints, from 0 to 10, which is shown in gray, we can then essentially understand what happens to an optimal solution. The optimal solution essentially tries to find an optimized point on this objective function. We refer to this as an unconstrained optimal solution. A constrained optimal solution uses the same objective function and variable control ranges, again let's say 0 through 10, and we apply a balance equation, here represented by y equals 20x minus 100 and shown with this aqua color line. The optimal solution therefore is no longer at the knee point of the objective function but somewhere on the balance equation line. This is referred to as a constrained solution. However, if we apply our objective function and our control variable range and we change the balance equation such that the balance equation is not intersecting the objective function curve, this solution is defined as an infeasible solution. We can see that there is no optimal point on the objective function that can meet the balance equation criteria within the control range. And therefore, the constraint has to be reduced or the balance equation has to be changed in order to find a feasible solution. The optimal power flow approach, therefore, allows us to define an objective function, apply bus voltage constraints, apply branch loading constraints, apply generator constraints, switching constraints, and therefore we can find our optimal solution in one shot in a direct manner. So let's take a look at our optimization setup. We first want to establish our constraints in the system. We would like to then select our control variables. We then define our objective functions, or in other words, what are we trying to optimize. We create our scenarios inside ETAP software and then run OPF and analyze our results. So it's a very simple 5-step approach in order to optimize your electrical system. Now, as we defined in the previous slides, the unconstrained OPF essentially gives us a solution that may be optimized, but without the constraints such as bus voltage constraint in this case. You can see the difference between load flow solution, where the bus voltages are 100% all the way to 97.23%, versus an unconstrained OPF solution, where we can see an optimized flow. However, the bus voltages are beyond the bus voltage limits. When we apply constraints to the same OPF solution, we can then see the same system has bus voltages that are now constrained to 105%, and we can now see a real and reactive power optimized solution and an appropriate dispatch on our generator. So what are bus voltage constraints? We normally define our bus operating voltage in percent, and we would ideally like the bus voltage to be operating at 100% of the nominal voltage. The constraint essentially could be an application of an upper limit of 105% and a lower limit of 95%. The constraint can also be uneven, which means that you can have an upper limit of, let's say, 103%, but a lower limit of 98%. So the constraint therefore doesn't have to be an equal 5% plus or minus. It can be an uneven value at the higher or lower limit. So let's take a look at the other type of constraint, which is branch flow constraint. The branch flow constraint can be applied in terms of amp flow or current flow, MVA, megawatt, or megavar. If you take a look at a pipe which represents the power flow in our electrical system, we can define our branch flow constraint with a base value. The base value could represent the rating or the capacity of the component, which could be a cable, line, transformer. We can define the branch flow constraint on the minimum side as constrained to 0, which means there is no flow allowed in this particular branch, line, cable, or transformer. We can then also define a maximum flow constraint, which is equal to a certain capacity of the line or a cable, such that we keep a certain amount of reserve and we don't reach the entire capacity of the branch or line. This is done to make sure that we have certain spinning reserve available in the system and or derating in terms of ambient conditions. However, just like bus voltages, the minimum and maximum do not need to be equal, or it can be uneven. So we can define our minimum constraint not only to be a lower value than the base, but we can also define that to be in the opposite direction. And ETAP allows you to do this. You can also define your maximum to limit the flow to 0 value. You can also set up your limit, the maximum limit, to be a certain amount of flow, again in the opposite direction. So all of these different combinations are available when we define our branch flow constraints. And again, if you remember the 5-step process, this is step number 1 in order to define the bus and branch flow constraints. Now that we've learned about constraints, let's go ahead and quickly apply those using ETAP software. We have a very simple single line diagram with a utility, generator, and an equivalent load with 2 parallel branches so that we can optimize our electrical system by adjusting the flow through various transformers and cables. We can simply run a load flow solution and observe the base load flow, or the initial load flow in this case, and then go ahead and run one of our scenarios that applies a constraint in the electrical system. Here we can see that the cable power flow is 5890 amps, and that corresponds to our branch flow constraint of 5980 on the maximum side. You can also see that the base rating of this cable is 6500 amps. So therefore we can constrain the flow through the cable less than its maximum nominal value or rated value. And this again could be because of requirement to maintain spinning reserve, or simply derating the cable due to other conditions such as temperature. We can go ahead and also apply another type of constraint in the system, once again on the cable, but this one is based on MVA. So we can go ahead and switch over our display option to MVA, and we can see that it's 24.9 MVA flowing through this conductor, which matches the maximum constraint placed on this cable based on an MVA unit. We can also apply another type of constraint which is based on megavar, and we can of course see that through our MVA display, but ETAP allows us to switch between megawatt and megavar. So you can see that the megavar flow is probably constrained to 13.5, and we can once again confirm that through our study case on the maximum limit. And finally, we can also go ahead and see another type of constraint on this cable which is based on megawatt. So here we can see that the cable is 21.8 megawatt flow, and that corresponds to our megawatt constraint of 21.82. Similarly, ETAP also allows you to apply constraints on transformers, and in this case when we apply a constraint on the transformer, which is an amp constraint, we can switch our unit over to amps and observe that the flow on the transformer is 125 amps on the primary, which is corresponding to 126 max on the transformer T2. And similarly, the other constraints can be applied as well based on amps, megawatt, megavar, and MVA for the transformers. We can also apply similar constraints on transmission lines, reactors, and generic impedances. Now let's look at step number 2 in our 5-step process. Step 2 is defining control variables. So here we are essentially defining the variables that we are allowing the optimization program to control, such as load tap changer settings, the range of the load tap changer in other words, generator AVR settings, or the reactive power that can be optimized or adjusted or dispatched from this generator, the generator megawatt, which is again the megawatt dispatch from this particular unit or multiple units, the series or shunt VAR compensator settings such as cap banks, phase shift transformer tap positions, switch capacitor settings, load shedding values, as well as DC line flows. The third step is definition of the objective functions. In optimal power flow solution, the selection of objective function is based on power system economy and power system security. The most commonly used objective function is cost of power generation. For thermal generating units, this objective function is generally represented by nonlinear second order functions. ETAP allows the users to define up to 10 multi-objectives, or in other words, up to 10 objectives at the same time. The purpose and application of course varies from industry to industry, and this is an objective function that can be applied for design as well as operations of the electrical system. But these 10 objective functions can be summarized into minimization of losses, minimization of power, minimization of fuel, minimization of control such as tap changer control, and of course maximizing security, which could be the flow security or voltage security in the electrical system. Our fourth step is to create scenarios. So we can leverage the multi-dimensional digital twin platform that ETAP already provides. You can create unlimited graphical visualizations such as unlimited one-line diagrams, use data revisioning where you can change the engineering data of your electrical system, and also use various configurations such as statuses of breakers, reclosures, as well as generators and loads. You can also extend this multi-dimensional database to keep track of sequence of changes such as multiple configurations, data revisions, along with sequence numbers as well as group numbers. Now, as you may recall, OPF benefits multiple industries such as power gen, power transmission, industrial facilities, and microgrids. So therefore, when we look at the OPF strategies, for example, for microgrid systems, we can leverage economic dispatch where we can improve power generation efficiency, balance renewables and system security, as well as minimize losses and fuel cost. We can use OPF to also manage our grid exchange control, such as balancing the grid exchange power, including setting limits such as net zero, improve voltage stability, and maximize voltage security at the same time. We can also use OPF for optimal asset operation, where we can minimize excessive mechanical movements, determine optimal set points over a broad range of functions, again such as tap changers and other mechanical equipment. We can also leverage OPF for a microgrid system to understand the impact of an islanded operation and then apply OPF to minimize losses and cost, maximize security, and of course optimize voltages. Let's quickly consider a microgrid system where we have a number of wind turbines, solar power generation, energy storage, a couple of loads, a diesel generator, and a grid connection. So here, essentially, when we run our load flow simulation, we can see the voltages vary from 100 all the way down to 97%. And we have import coming in from the grid, which is 3.4 megawatt, and the diesel is generating about 1 megawatt. Of course, we are not necessarily controlling the PV and the wind turbine output because they vary based on irradiance and wind speed accordingly. So we'll focus a little bit more on the diesel and the grid exchange power. If we look at the losses for this particular system, we notice that the output report in ETAP gives us the total system losses, the real power, which is about 0.1 megawatt and 0.3 megavars. So when we switch over to optimal power flow and run our OPF solution, we can see that the diesel is generating about 1 megawatt and our grid exchange is set to 0. Now this may look absolutely perfect. However, if you notice the voltages, they are very low. They are around 50%, which is unacceptable. So the first thing that we would normally do is set up the bus voltage constraint, and we can set up bus 2 to be constrained within 97 to 103% and go ahead and rerun our simulation. And we of course come back with our problem being infeasible. So therefore we need to put some controls. So we can go ahead and put our control in for the transformer taps and rerun the calculation to see if that helps us improve the voltage. And in this case it doesn't. So we try one more technique which allows us to vary the generator and the utility reactive power as well as the real power in the system. And we can go ahead and run our simulation now, and we do get a solution where the voltages are within acceptable ranges and the generator and the utility are actually right now balancing the power that they are generating. Now the power that they are balancing is based on a couple of objectives, and the objectives are set up for real reactive power loss minimization but also for fuel cost. So therefore the dispatch is now done based on 2 megawatts roughly each. And if we go ahead and look at the summary report in terms of our losses in this system, we expect some minor improvement. So we essentially see about 0.137 instead of 0.155, and our reactive power is also slightly lower. So that's one quick way of looking at a microgrid solution and establishing an OPF solution that works well for this network, and then start optimizing other constraints and controls in the system to get a more optimized power flow in this type of network. Now when it comes to industrial optimization, OPF has many advantages. You can use it to optimize the fuel mix so that you can improve power generation efficiency, balance that mix along with the system security, minimize the real power losses, and of course find the best fuel cost in terms of power generation. You can also control grid exchange power by balancing the grid and improving the voltage stability by also adjusting the reactive power. And by adjusting the reactive power, we are also maximizing our security. We can also utilize OPF, just like with microgrid systems, for optimal asset utilization, where we are minimizing the excessive mechanical controls that may be used to optimize the system. And then we can also use OPF for capacity derating. So if there's temporary maintenance in the system, or there are other factors that are causing a particular asset to be derated, then you can essentially set up OPF to set up various constraints and then optimize the flow within the network such that you are minimizing the losses and improving the system security. Here we have a quick example of an industrial system where we are essentially looking at 2 generators in the network along with the industrial loads and 1 utility connection. So when we switch over to our load flow analysis and run our simulation, we can see that there is a certain amount of power being generated by generator 1, about 3 megawatts that's being imported from the grid, and about 8 megawatts from generator 2. So 11, 8, and 3 approximately. And the amount of losses from this particular network can be observed inside the summary report that we can go to the last page, and we can see that the apparent losses are about 140 kilowatt and almost 1 megawatt in the system. However, we'll focus a little bit more on the fuel optimization and see how OPF balances our 3 different sources. So we can essentially set up the fuel cost within each source. The fuel cost is set up within the generator, for example, and it can be heat rate versus output or cost versus output. The fuel type can be established based on a piecewise, which is pointwise, equation, or V-curve based. And you can also define the fuel cost profiles, which ETAP allows you to define about 10 of them. This lets you manage not just one fuel price, but multiple fuel prices, especially if your generator is capable of running on more than one fuel type. And you can decide what the fuel type mix should be by entering in the blended cost or the individual cost of the fuel. The cost curve gives us the cost in dollars per hour versus the megawatt output, and you can also see the incremental cost. The numbers are purely there for representation. They do not represent a real system or a real generator, but of course these would be substituted with the fuel cost from your generation system. You can also define the operating limits, which may be beyond the values that are based on the nameplate of the machine. So if your generator is 13.28 megawatt, you can define an operating range that is slightly tighter, including certain prohibited operating ranges. So let's take a look at the utility price, which is the energy price from the grid, and this is defined also based on a piecewise model. And you can also define the minimum and maximum dispatch for the grid that you want to constrain or limit the utility power. The model parameter also gives us a piecewise value of the cost per megawatt. What is the cost per megawatt hour? So you can see the price and the incremental price in dollars per megawatt hour as well. So the first scenario that I've already created in the interest of time is when we want to minimize the cost on the system such that the generator 1 is actually the cheapest source, while generator 2 is actually not the cheapest source. So here we can see OPF rebalancing such that we are using generator 2 purely for its reactive power and not the real power output. The grid power goes from 3 megawatt to 8.6, and generator 1 takes up maximum load and reaches its rated limit of 13.281 megawatt. So this is a case where we are setting up the program such that generator 1 is the cheapest source of energy and you can see how OPF rebalances or redistributes this within the network. Now when we switch over such that generator 2 now happens to be the cheapest source, you can see generator 1 megawatt going to 0 and generator 2 picking up almost 10 megawatt while the grid actually picks up 11.2. And this is a case where there's a blend between the energy price on the grid and the generator power. So they're not dispatched the same as generator 1. And finally, when we have our generator which is expensive, both generators are expensive. So in both cases, the real power essentially goes to 0 megawatt, and we are using them again purely for the reactive power. And maximum power, almost 22 megawatts, is now actually coming from the grid. So this could be a case where we have switched the fuel on the generator, and the cheapest source based on the energy price and the loading of the system happens to be the grid. Now these are all snapshots in time, and when we look at the operate side, we can see how this dispatch works on a continuous basis. Let's take one more example of an industrial system where we essentially have a power grid. We have a couple of industrial motors in the system. We have 2 different generators here, and a number of other miscellaneous auxiliary loads in the network. Now in this case, we'll take a look at what happens when we are trying to use OPF to just improve our voltage only. And here we can see that in certain parts of the system, with the magenta color, you can already see that there are certain buses that are under voltage in the network, and we want to have a bit more of a flatter voltage profile in the electrical circuit. Now we can quickly see what's going on by turning our color contouring on, and we can see the orange and the red patches are essentially telling us where we have lower voltages in the system. The green area, everything is perfectly fine. That means it's close to nominal values. And if you see any of the blue colors or bluish colors, those are areas where we can see this slightly over voltage, but not by much. Now in this case, this is our base case that we are running, which is through load flow. And I've already set up OPF to flatten the voltage profile, so we can see what happens when OPF runs. So those the orange red areas have essentially been eliminated and replaced with slightly bluer areas, which means we are slightly over the nominal values, and we can zoom in and see how much over. We are at about 102% or so of the nominal values. And this is basically OPF trying to use the various controls that we have in our system to get to these healthier voltage levels. You can of course see the controls and constraints and the optimal settings through the output report. And here we can see within the crystal report what the generator A, C, and utility power levels are supposed to be, and in terms of the optimal settings. When it comes to applying OPF to power transmission or utility transmission systems, the strategies are very similar to industrial systems once again. So that includes capacity derating, especially for overhead lines, optimal asset operation, so minimization of control of various mechanical components. Economic dispatch is a very strong driver for transmission, where we are balancing losses and fuel cost to achieve an optimal economy of the power transmission operation. And we're doing this through a multi-area control. So that basically differentiates the transmission OPF strategies from the industrial OPF strategy. So let's take a look at a quick transmission system. This is one of the examples that ETAP provides. This is a multi-area transmission system where we have each area represented by its own breaker and half scheme as shown here, here, and so on and so forth. And within each of these areas, we have generation and load centers. We can see one generator right here. We have another set of generation system represented here, followed by another area here where we can see that there's additional detailed loading shown for this industrial customer with multiple composites that go into more detail. The transmission system in ETAP is represented through a bus breaker topology. So we essentially have a full electrical system model for design. That's the same model that ends up being utilized by the EMS system. And we can switch over to our preferred theme so we can see the information in a bit more crisp and concise manner. Now, in this particular system, we can go ahead and run our load flow calculation, and we can see the power flows in the network. But of course, we'll focus again on the summary so you can see where the losses are in our network. And at a holistic level, we can see that the losses are about 12 megawatts in this network. So if we go ahead and switch over to our optimal power flow solution and run the simulation first, and then open up the study case so we can see what our objectives are. We've set up the real power loss and the fuel cost as our classic economic dispatch. We'll eliminate the flat voltage profile for the time being, and we can see that we've set up our constraints. Our branch flows are actually unconstrained. We have load tap changer adjustment, generator AVR and megawatt adjustment, and we don't really have any shunt devices like capacitor banks or SVCs in this network. So when we run our calculation for optimization, we can look at our bus voltage here, for example. We notice that it's at the lower end of the constrained bus voltage limit of 95%. And when we look at the summary of our optimal power flow, we can see the losses have been reduced from 12 megawatt down to 10 megawatt. So we have about 2 megawatt of saving in this particular system with these assets. But the primary saving is through the fuel cost, because that is the secondary objective that we've established in this system. However, this is not very good in terms of voltage security. So what we would like to do is come back into our objective and flatten the voltage profile, which means through all the controls that are available in the system, we would like OPF to essentially bring the voltages closer to the nominal values on every single bus in the system. So when we rerun our optimization again, we can see OPF trying to bring the voltage back up to 100%. And in some cases, it will achieve that value, and in some cases, it may not be able to achieve that value. So we are getting closer to 100%, but not quite. And this is where you start tightening the constraints so that you bring certain critical buses up to its nominal value in a more focused manner. Now, when we go back and look at our summary and see whether that has impacted in any negative manner, we can see that no, we still have about 2 megawatt of real power savings in the system, and we have managed to bring the voltages within a flatter profile of 100% throughout the system, while bringing in generation economy and of course keeping our voltage security closer to 100%. Now, if you recall, I mentioned in the beginning of the webinar that OPF is a requirement from design to operations. Now, ETAP completes your end-to-end journey all the way from design to operations by taking this digital twin that we've been looking at through our single line diagram and all the richness behind each asset, such as the fuel cost, the rating of the generator, the capability curve, and so on and so forth. All those information, the characteristics of each and every component is used in the as design stage, and we're using this as design stage for our optimal power flow solution and analyzing our electrical system, which could be done during feasibility or detailed engineering phase. But you can transition that digital twin model all the way into operations using ETAP real time. So then that model becomes the as operated, or in our case, the as optimized electrical system. And we can use this then for economic dispatch of the various assets in the system, as well as optimized control of adjustable devices such as tap changers and cap banks in the electrical system on a continuous basis. Again, if you recall, I had mentioned that when we are running our OPF calculations, we are using a snapshot of the electrical system, and we rely on various scenarios that we establish as engineers to optimize the system under different conditions. But what if the conditions are changing such that we did not anticipate, or we did not include all the conditions as part of our analysis? So therefore, when we apply OPF using ETAP real-time, we are essentially stepping into the realm of automatic generation control, economic dispatch, and unit commitment, which is then running on a continuous basis, and we are able to optimize the electrical system not only based on daily operation but also weekly, monthly, yearly, as well as sometimes hourly basis, depending on how quickly a system can change during each stage. So how do we actually take this digital twin model and connect it to the real-time data? So of course we are using data exchange to bring in a lot of information into the model to generate that single line diagram and that digital twin. We are using the mobile app and the cloud PM platform to collaborate and build up on this as designed model and field verify through the mobile app all the data that's actually out in the field, especially if it's a brownfield site. We have various deliverables. We've looked at reports, we've looked at our single line diagram, but there's another set of reports such as SCADA, GIS, plots that you can leverage in ETAP to generate various deliverables, again from your as designed model. But then we bring in real-time data through various protocols such as 61850, Modbus DNP3, SIM, and also connect to other SCADA systems through OPC-DA or OPC-UA protocols or ICCP, especially if you're dealing with transmission systems. And then we run these analytics on a snapshot basis or on a continuous basis and provide you with an optimized solution for your electrical system. So before we get into a practical example again, let's take a look at economic dispatch. Now when we look at economic dispatch, it's just a single part of a secondary control system. We normally use operating frequency, generation, the actual interchange, as well as the target or schedule frequency for load frequency control to regulate and dispatch the generators, such as raising and lowering the generation levels. And this is a secondary control loop that ETAP has when you're utilizing real-time data in the electrical system. You can bring in interchange scheduling, which allows us to establish various exchange power controls or exchanges between different control areas of the electrical system, or it could just simply be an interchange schedule for your microgrid or industrial system where you want to adjust how much power you're buying or selling to the grid at various different points in time. The interchange scheduling, plain and simple, is the tie line control that you're bringing in to the mix along with the frequency control from various generation sources, and then dispatching the generators accordingly. Economic dispatch comes in and provides that monetary component where you're looking at system constraints, generation fuel cost, the economic limits, and the cost curves as we saw earlier in OPF to run those on a continuous basis. So with economic dispatch, we're trying to find the cheapest energy source closest to the load center, and when we bring that into our mix, we are also managing frequency control and honoring our exchange of power, buy or sell contracts, and then dispatching the generators accordingly. And then while we are dispatching this, we have to look at real-time regulation limits that may be established by the operators. So therefore, the economic dispatch looks at the cost curves of various generators in the system, and then it's finding the cheapest energy source with the least megawatt losses, which means again the cheapest generator that is closest to the load that's consuming power. Since we have been using this transmission system to look at load flow and optimal power flow and see the differences between them, we can use the exact same system and take it online and see how OPF works when we are connecting it with real-time data for continuous optimization of your electrical system. So this is essentially the offline state of our electrical system, and here is the real-time state of our electrical system. There are of course different quick shortcuts available to the operator to get to various aspects or various parts of the facility, such as the gas plant or a power plant. These are essentially just shortcuts provided to enter the composite networks. So for the time being, we'll minimize this. And as we zoom into a particular section of this electrical system, we can see that the system has more data on it. The data includes this aqua color, which represents the meter reading, which you can see roughly changing once per second, and a power flow that is being calculated, again, roughly once per second, which is the state estimator output. The state estimator is essentially not only looking at the meter measurements to analyze the state of the electrical mesh, but it also is doing a load distribution. So you can see the state estimator output all the way down to the last load in the electrical system, all the way from high voltage, medium voltage down to the low voltage circuits. The state estimator has many advantages, but here the primary advantages are the ability to determine the pseudo measurements and fill in the blanks, such as the voltages on bus bars that do not have measurements. The state estimator also allows us to compare the flow of the state estimator, or the calculation from the state estimator, along with the meter values. So based on the deviation between them, ETAP can quickly tell you through a comparison table in this deviation column how good or bad is your model with respect to the real-time data, and allows you to tune the model so that you are making good decisions based on a strong foundation of your electrical single line diagram. However, we will use the state estimator here as the foundation for running our optimal power flow. In the background, the optimal power flow that runs on a real-time basis will use the initial conditions established by the state estimator. If you also recall, I had mentioned that ETAP allows you to have multiple presentations. So we can quickly switch into our AGC mode that includes not just AGC but also economic dispatch. And inside this particular presentation, which is a copy or a parallel of the presentation where the operator is looking at their monitoring values, we can switch this particular presentation into our real-time system, switch over into AGC mode, and then go ahead and start establishing the AGC control parameters, just like we did for OPF. So we can determine the cycle time for our economic dispatch, which again, remember, it's predominantly real power loss and fuel cost optimization. We have other objectives such as power sharing, unit commitment, and frequency control. We can set up our optimization solution parameters here along with our fuel cost, and define our objectives. And you'll notice that these objectives are exactly the same as the OPF that we used during design stage. And there are additional objectives such as frequency control, power sharing, and unit commitment. We can define certain frequency control parameters here, as well as generation control parameters, but predominantly here we are focusing on economic dispatch, so we can see that we can set up economic dispatch for our generators for megawatt and megawatt both. And we can determine which megawatts are constrained. We can also establish the AVR constraints, the bus voltage constraints, just like we did in OPF, as well as the branch flow constraints. So the setup for economic dispatch is the same as optimal power flow. It allows you, however, the flexibility to not just do real and fuel cost optimization, but you can mix between any other optimization when you are running in real-time mode. So let's go ahead and run our AGC in real-time mode. And while the AGC is running on a continuous basis, we can look up our AGC monitor that tells us very quickly for each area within the electrical system. I have generation and interchange, and within this generation and interchange I can see which generators are actually being controlled, shown in green, and what is the economic dispatch being determined for each unit. Of course, the operating parameters are shown here, which are updating on a continuous basis. The area control error and the target frequencies are determined based on the frequency control, which is running every few seconds. And every few minutes, we are running an economic dispatch that overrides or supplements this target that is being dispatched for frequency control. So with this, you can clearly see that you can take a model which is in as designed mode, run optimal power flow, get an optimized state of your electrical system as designed, or in case of an expansion or retrofit of an existing facility, then transition that model into real time and use exact same settings to run the optimization as well as other types of controls on a continuous basis. And these types of controls can be in advisory mode, where you're just advising the operator in terms of what set points or targets to dispatch, or they can be in supervisory mode, where the AGC program, along with economic dispatch and unit commitment, are in a closed loop mode, dispatching the generator on a continuous basis. Now, of course, there are a lot more details to OPF than what we can cover in this webinar given our limited time, and we do encourage you to attend an ETAP workshop which can give you more information about this particular module and get you more hands-on training. In summary, ETAP OPF allows you to define multiple objectives simultaneously with a weighting factor. It uses a sophisticated interior point method with logarithmic barrier functions, and it allows you to minimize power losses, active power optimization, reactive power optimization, has automatic infeasibility handling where you can relax certain constraints or stop the calculation depending upon your preference of performing the analysis. It also allows you to handle inequality and equality constraints and allows you to define controlled solution parameters. ETAP OPF has comprehensive objectives and constraints. It gives you access to an accurate AC system model, which is exactly the same model that you would use for power flow, fault analysis, protection coordination, contingency analysis, voltage stability. It's the exact same model, and therefore it also allows you to increase system efficiency by applying the optimization routine on the same electrical system. Through minimizing fuel cost and minimizing real reactive power losses, you can reduce your operating costs based on the energy savings. You can improve electrical system performance by finding the optimal positions for various controllable devices and therefore increase reliability of the electrical system. By optimizing the reactive power, you can strengthen system security, and you can use OPF not just for short-term purposes but also for long-term planning objectives, where you can include scenarios such as additional load growth as well as new substation additions in the system, and of course use the OPF calculations not only in system design but in operations as well. We hope you got a good flavor of the ETAP OPF analysis in this particular webinar, and we look forward to seeing you in other future webinars as well as the ETAP workshops. Thank you once again, and hope you have a safe and pleasant day.